So let's start explain DC series motor. What is the difference between DC series motor and the other motors? You observe here that's the armature and that's the back EMF. It's called EA, and that's RA, the armature resistance, which means the rotor windings resistance, and then that's the field resistance. So you connect the field winding in series with the armature. So the voltage source, VT, is going to supply both winding, the field winding and the armature winding. And usually we add resistance in series so we can control the current. What current we're talking about? In this case, armature current is equal to the field current because they are connected in series. That's very important, and that's the difference. So in this circuit, IA and IF, they are the same, connected in series. Let's find the relationship between the speed, the current, when I say current, armature current, and the torque. The first thing we do in any machine, in any DC machine, we have two essential equations, right? One for the back EMF and one for the torque. Let's look for the back EMF, EA. It's equal the machine constant KA time the flux time the speed, angular speed. And we know that phi, the magnetic flux, proportion to the field. So we can write it like KF times AF, IF. The field current produces the magnetic field. So we can say linear relationship. It's not completely linear, but just we'll assume it linear to make the analysis simple. In this case, the field current is equal armature current. So I can replace IF by IA. Clear? That's the only difference in series machine. But it will have tremendous effect on the machine characteristic. So the back EMF, I can write it like now, KA, and phi, I will replace it by KF, IA, omega M. KF and KA, it's constant. Let me call it KS. So remember that's for the series. They are constant. IA, omega M. That's the back EMF. Let's now find the torque relationship. T equal to the same thing, the constant, Ka, machine constant, times flux, times Ia. So I replace the flux by Kf, If. And then, but If in this case is equal Ia. So just I replace If by Ia. Now I call this already constant Ks. So I have Ks Ia square. That's the torque relationship with the current. I'd like to find the relationship between the speed and the torque, as we did in the shunt or separately excited DC machine. And I will refresh in memory the characteristic that we got in DC shunt machine. That was the torque, that was the speed. That was the initial speed. It was like that. So almost the speed is constant. We said that the regulation is really very small. Now, I'd like to find this relationship. How I find what's the relationship between the voltage VT and EA? In this case, we know that the voltage, the terminal voltage VT, will equal EA plus the drop across all the resistance. So I would say IA times the armature resistance, the field resistance, and let's say the connected in series, call it the SR, the all resistance connected in series. So to make it simple, I will say EA plus IA, and the all resistance, I will call it RS. The total resistance in the circuit, RS. That's the terminal voltage. I can find now E. is equal to VT minus RSIA. What's EA? We found EA in this equation. It's equal KS. Let me just do on the side here. We found EA is equal KS IA omega M. And we have the torque equation, T is equal KS times IA squared. Yes?
This is the equation we're going to use. Is this for a shunt motor or series motor?
I'm working on this series motor. Yeah. That's the series DC motor. I'm writing the same equation I just derived here because I want to find the relationship between. I don't use the armature current. I want to use the torque. From the torque equation, I have the torque equal to KS IA square. So from this equation, and I can find IA. IA square is equal torque divided by KS and then square root. That's IA. So I can put IA in this equation of EA. So EA is equal to KS, and IA is square root of T over square root of KS times omega M. KS, so I can write like that, square root of KS, because I mean KS, it can be written like KS square root, right? So I can cancel one of the bottom, and then I have square root of torque omega M. That's, I mean, EA, this equation of EA. So let me just write here, we found EA is equal square root of KS, square root of T, omega M. That's the equation I found in. So EA is equal VT minus RSIA. I go back to the circuit, and I will replace EA by the equivalent. So right here in space. So I have EA, I will replace it by the equivalent, square root of KS, square root of T, omega M, equal VT minus RSIA. I'm interested to see omega M, how omega M changed. So I will divide the old equation by square root of KS, square root of T. So it's equal VT divided by square root of KS, square root of T, and the second term, RS, and I have IA. Oh, I can replace also IA by the equivalent. That's IA. Okay, so IA, it's equal square root of T, square root of T, divided by square root of KS. I still need to divide by this term, square root of KS is square root of T. So what I got here, that's omega M. This term is constant. The voltage supply is constant. KS is constant, so square root of KS is constant. So you can say that's omega M. Omega M is equal to constant divided by, call this constant A, because we are going to have two constants, A divided by square root of T here, minus RS, the second term, RS constant, and this cancel. So we have RS constant and square root of KS You multiply, you get Ks, which is constant. So the second term, it's completely constant. So I'll call it B. So that's the question I got. And then simplify. It's constant over a square root of t. How you sketch something like that? How you sketch if I ask you to sketch y equal to 1 over x? It's the same like square root of x. How you sketch it? 1. If you put x equal to 0, you say 1 over 0. That will give you infinity, right? So becoming, if this is x and this is y, so you're coming from infinity. When x getting big value, great value, infinity, if x equal infinity, 1 over infinity is equal to 0. So it'll be like here. So the curve of 1 over x, it look like that. Y inversely proportional to x. I have a very similar. A over a square root of t. So t, when t is equal 0, square root of 0 is 0, so be infinity. So maybe somebody ask about what's about negative b. This constant. Be constant, make it shift to the curve. That's all. But still having the same shape. Because if you have this infinity, and you say infinity minus 10, what you get? Infinity. And this one will be 0 minus b, that will make different. Okay. So we sketch it. There are many curves here. It depends on the series resistance that you change. You remember we said that there's a variable resistance we add to the circuit. So when you change this value, you change the value of B. 1 time minus 1, minus 10, minus 100, whatever. So every time you are increasing this resistance in series, the curve is moving in this direction. So if you have Rs equals 0, so this is the curve you're going to get. If the series resistance equals 0. If you add more resistance series, you find the curve just, it's taking the same shape, inversely proportional. It just shifted towards the origin. So that's the characteristic, completely different than the DC shunt. When we study machine and we study the change of speed with torque, we are not just studying this just to sketch curves. No. To find good application. So when you choose a motor, you choose the motor according to the application that you need. For example, this is the characteristic for DC shunt or separately excited. You observe that the speed does not change much. So if you have application that requires constant speed, most of the time does not depend on the torque, so that would be the good one. If you want something to rotate in constant speed, that's good. Do we have something like that? Yes, we do. If in my internship, I went to a company that they have like rolls or drums, and they try to make thin sheet, and you want to keep this thin sheet, the thickness of the sheet, constant. Not, I mean, just bumpy in some side. No, you want to be like smooth. So the best thing to do, you have something like that. If you need constant speed, constant pressure, so use something like that. But this machine, what we're going to use? Let's investigate the characteristic, the speed against torque. What does it mean? Okay. First of all, what is the relationship between the speed and the torque here? If you pick any curve, let's just have one curve. That's the speed, and that's the torque. And it's like that. If we pick torque in this, let's say T1, that will be the speed, omega 1. If you increase the torque, what happens? The speed gets low. So that's good for what? You want something that when you need big torque, the speed will be less. So what application between them? Top of grade. That's possible, yeah. Yeah. and maybe in hoist, like when you look at the, in fact, you find hoist or in a traction application vehicle, all hoists and cranes. When you drive car and you go uphill, what you need, you put it on the low gear, right? That would be like the speed will decrease, so you can have big torque, so you can go uphill, you know. So you need something like that. So that would be good. Not the DC shunt or cycle. You need big torque. So, and the speed will be lower. So that would be good. So that's why, I mean, used in crane. More than that, there is something else that you can find in the characteristic we just found. And you don't need too much current to produce torque like shunt and excite. Why? You don't need too much current. Like if you need, let's say that you need 16 amp to produce torque in shunt or separately excited, this one you need only 4 amp. Do you know why? Exactly, because when you look at the torque, that's good. When you look at the torque here, you found out that the torque is proportional to IA squared, to the square of the armature current. So 4 amp means 16 when you square it, that will be equivalent to the other. So you don't need too much amp. That's good. Let's discover more of this characteristic. And when you look at the starting current, many machines, many applications, most of them, they need high starting current, high starting torque. This one, it does, you know, because if you look at the low speed, you'll find the torque is high. I mean, I'm sorry, when you find that the speed high, the torque is low here. So it has like high speed when you start. But there is something dangerous. You cannot, why I'm going to say, what's dangerous about this machine? Something dangerous, you have to be cautious, especially when you do in the lab. The experiment with DC motor, you have to be very cautious. What is that? No, I mean, this is for all machines, even in shunt. It should not exceed 2 amps. Okay. Look at the characteristic. Just what do you think? What do you think that would be really dangerous? Is it too fast? Yeah. Why would it be too fast?
Well, if we're looking at that, if the speed goes too high, it'll out.
When it will be too fast? You are close to that. When is going to be too fast? Yes. Yes. Let's start. Start. And I equals 0. Torque equals 0. Speed will be infinity. The machine will be broken and be jumped in our face. That's true. That's true. So what is the solution? How we can avoid it? Well, let's not talk about current. Yeah, you're closer. Yeah, we don't start with I0. What does it mean?
Never have it open. Always have it.
No, we don't open.
Pardon? Start the torque on.
Yes, never start DC motor without load. Put the load and start. Yes, any load, put the load. Don't start with no. You start with no load. That's the difference. So that's the precaution that you should be careful. I think now, I mean, we'll cover the characteristic of the DC motor. Okay, and now let's just take one example to solve. We have a DC series motor, 7 horsepower. That's the power output, I'm sure. 220 volt, that would be the terminal voltage or the armature. Is mechanically coupled to a fan and draws 25 amp and runs at 300 RPM when it's connected to 120 voltage supply with no external resistance. Okay, so they didn't add any resistance. The armature resistance. Okay. The torque required by the fan is proportional to the square of the speed. That's another thing important. You got to know what the characteristic of the load that you connected to the motor. So the fan He said that the fan, that's the DC motor, that's the shaft, and that's the supply. And you supply it by 220 voltage, and then you put the fan, which is the load. And the fan characteristic is the torque of the fan is proportional to the square of the speed. Okay, that's the characteristic of the fan. The armature resistance of this DC motor, RA, is equal 0.6 ohm. The other resistance, 0.4 ohm. That's the field, obviously, the series field. Neglect armature action, okay. And the amp that's drawn 25 amp, drawn from the source, and drawn, and the speed is running 300 RPM. Okay. So the first thing, determine the power delivered to the fan and the torque developed by the machine. So we need the developed power. That's part A. And the torque. And when you say it's developed torque or electromagnetic torque, because how do I know that? Said the torque developed by the machine. That's not in the shaft. I mean, ignoring that, it means we're not going to take into account the rotational loss thing. No, just produce at the armature. All right. Okay, somebody help me. How can we find how we can calculate the developed power? Developed power. We did that with the equations. Developed power means in the armature. You don't have to think about too much. It's produce the armature. What the armature voltage and current? EAIA. So to find the developed power, let me just sketch the equivalent circuit first for the series DC motor. That's the armature. And that's the resistance of the armature. And that's the resistance of the field series. And that's the supply, VT, IA, EA. So the power produced here should be equal to, the developed power should be equal to EA times IA. IA is given already 25 amp. So IA is given 25 amp. But you don't have EA. How you find EA? You write just the equation. The equation in this circuit is very simple. VT is equal to EA plus RA plus RSIA. VT is equal to 220 voltage. EA, I need to find. RA is equal to 0.6 is given, plus 0.4, and IA is equal to 25 amp. From this equation, calculate EA. That's the first thing. So EA is equal 195 volts. That's the first thing. And IA is given 25 amp. Now we already calculate the developed power. So developed power PD is equal to EA times IA. It's equal to 25 times 195. You get the power in watt, which is equal to 4,880 watt. Okay. Now we found the developed power. What's supposed to get next? Developed torque. How you find developed torque? Simple. What's the relationship between torque and power? Somebody answer. Developed torque, developed power. The relation between power and torque, mechanical. What's the relationship? Power equal torque times omega. Power, said that before. Power equal torque times omega. Mechanical. Power in electricity, E, which is voltage, times current. In mechanical, torque times omega. So I want to find the torque. So the developed torque or electromagnetic torque is equal to the power divided by omega. Do we have omega? We have the N. We can get it. So the developed power is equal 4,000 or 880 watt divided by omega. How you find omega? Omega is equal to pi m over 30. So pi times n, 300 RPM divided by 30. That's it. You get the torque. 155.2 Newton meter. That's the developed torque in the armature here on the shaft before it go out for the rotational loss. So that's the first part. The simplest thing. You got to practice the exercise in the full. B, the speed is to be reduced to 200 RPM. Now you want to reduce the speed from 300 RPM to 200 RPM by inserting a resistor. Now it's going to connect a resistor in series in the armature circuit. Determine the value of this resistor and the power delivered to the fan. That's a very practical problem. You want to control the speed of the fan. So they added another resistor here in the circuit. Call it RAE, whatever. So what is the value of this resistor that you're going to add? So you reduce the speed from 300 RPM to 200 RPM. Need to find the resistor. How we think about, yes?
Wouldn't you kind of do the process first because you're given that in the main part of the question that torque is proportional to the speed squared?
Yes, torque is proportional to the speed. Okay. Okay, that's right. You get the torque, the new torque, that's right. And then, that's right. So that's true. Torque is given proportion to the speed. And also we know in the DC motor, the torque developed by DC motor proportion to armature current square, right? IA square. So we know this relationship. And if we want to find, let's just investigate it. And we know that the torque in DC motor proportion to IA square. So it means that the torque, we said is going to be equal K, we call it Ks, the whole constant, IA square. So that will help us to find the constant Ks. That's the first thing. I need this constant. Why you need this constant? Look at that, what we did here. When we found that the relationship between torque and current, it's Ks, between the EMF and omega, we have also Ks. The same thing, Ks is Ka, Kf. I'm not interested to find Ka and Kf, I just want to find the relationship because Ks will help me to find the EMF. It will help me to find EMF. Why I'm interested in EMF? Because the speed will, when the speed will be reduced, the voltage will be reduced, and I have the circuit, and then when I have the circuit, I have the voltage, I have the current, I have the resistance. To find resistance in general, to find resistance, Ohm's law require two variables, voltage and amp. That's enough to find the resistance. That's how we're going to think about. Okay, voltage and amp. What is the voltage is affected by the speed? EA, the back EMF. So that's why I'm looking for the O relationship that will help me to find the EA, the back EMF. So Ks, obviously, it's in the it's the relationship between the torque and the current, and also the relationship between the voltage and the speed. So Ks will help us. So let's find Ks. And we'll find Ks from the previous case. The torque was given, we already got it in the 155 We have it before 155.2, and the armature was 25 M. So that's the first thing we do. So KS can be calculated 0.248. That's important. Found the constant that will help us. Now, when you reduce the speed to 200, you can find the new one, because torque now is you can write like you have T2 and T1. All right, that's the torque. T2, that's for when the speed is equal to 200 RPM, and T1 when the speed with 300 RPM. We got this one, T1 when the speed was 300 RPM, found that T1 is equal to 155.2. That we got it here, Newton meter. But the torque when the speed 200, we don't know it. And we know, as you said, that the torque given for the load, the fan, proportion to the square of the speed, right? Let me just write here, torque is proportional to the speed square. So what does it mean? T2 over T1 is equal N2 over N1 square. Simple. From this equation, T2, I don't know it. T1, I know it, 155.2. Into the new speed is equal to 200 RPM, and the old one was 300 RPM square. And then I find the torque. So the torque, the new torque will be equal 68.98 Newton meter. If you wish, you can go step by step to find everything, or you might like to use the equation that we found here. We found the equation omega m is equal a over root 2 square root of t minus b, and you have the all details like the v term ks. We found it. Torque, we found it. We have it now. The new one, rs, that will be the unknown. That's the total resistance. And Ks known. So for using this equation, you can find everything. Using this equation, it can tell you about the missing term Rs. But if you don't like to use this equation, you want to get it like step by step, you still can do that. Because you can say, okay, if some people are comfortable with the simple thing, like let's say, okay, I know the torque, I can find the corresponding current. How you find the corresponding current? We know that the torque, we just use the equation, the torque is equal, here just with it, Ks Ia square, right? From this, I can get Ia. Torque divided by Ks. But now I'm finding the new armature current corresponding to the new torque, corresponding to the new speed. The new torque I got at T2 is equal 68.98. Divided by Ks2, we got it here is equal 0.248. That's Ia2. I got the Ia.
Doesn't it have to be square rooted?
Exactly, yeah. If you have calculator, you can give us the, please, if anybody has a calculator, can get us the value for Ia. Well, it's according to my calculation is equal 16. You can check if it's correct, 16.68 M. That's the new, the first one was 25 M. So does it make sense that the current will decrease? Yes, it makes sense. Why? Because torque decreased. Why torque decreased? It's proportional to the speed square. Speed decrease, torque decrease, current decrease. Okay, so it makes sense. That's why I always check your answer. Does it make sense or doesn't make sense? Then you review. It makes sense. So I think it's okay. Now, what I want to find, why I'm doing that, why I'm getting the current, because I know that if you look at the equivalent circuit here, this voltage and this voltage, the difference between these two voltages will be across the resistance, and that I need to find the resistance. So I know that VT is equal to EA plus IA, RA plus the R field series plus the additional resistance that I don't know it. I want to do to control the speed. Now it's getting clear. The terminal voltage never changes, 220 volts. The EA, I'm going to get it. Why? Because this is changing with the speed. What is the equation of EA? We just got it. Let me show you the equation that we got it for EA. EA is it's proportional to IA and omega M, and KS we already got it, right? So EA, just right there, EA is equal KS IA omega M. KS it's equal to 0.248. IA, the new armature current, I got it 16.68. 16.68. Omega M, we know the speed. The new speed is equal to 200 RPM. I will change it to 200. I multiply by, I divide it by 30. I got EA, all right? So I put the all, whatever I got here for EA, which is equal, I did the calculation, is equal to, I think 86.57. So I put the value here, 86.57. Plus IA, it's IA, the new one. The new one. I'll make two to make the new one. The new one is 16.68. All right. The armature resistance is equal 0.4. The field 0.6. RA, the series one to adjust the speed. I don't know it. That was the unknown. So now that's the equation that I was looking for in the beginning. But to get it, I got to see. I mean, look at the equation. This equation, I have it here. I want to get RAA. So in this equation, I should know IA2, EE2, V terminal. V terminal, no problem. It's the same voltage, never change. EA, I have to find its equation. KS, IA, omega M. So I need to calculate the armature current. The speed is given. KS, I found KS, the constant, from previous case, because KS is a constant, does not change. That's why I started the problem to find the constant, because I will need it. And IA, I calculate IA. How I calculate IA? The relationship between the current and the torque. Because always we said there have two essential equations in DC machine. It doesn't matter shunt or series. The voltage, the back EMF, which is proportional to the speed, and the torque, which is proportional to the current. So in this equation, just you solve it, you get the value of the unknown RAA, the series one. If you do that, that would be equal to 7 ohm to reduce the speed. If you want to find the developed power, it's easy. Developed power, how you find developed power? Multiply the voltage times current. What voltage? EA. What current? IA. What you get? Developed power. So the developed power in this case, PD is equal EA, IA. We have EA, I just got it here, is equal 86.57. And the new armature current, we got it 16.68. In this case, you get the developed power, which is equal to 1,144. That will be in watts. You can change it, of course, to horsepower if you like, but that's the developed power. That was the in part B that was required. Yes.
I'm still confused about the relationship between speed, torque, and current, because in part A, we had a higher RPM and it's a higher current. But then when we made the RPM slower, we took it down to 200, then we got a lower current and a lower torque. I thought that we have like higher current speed drops and the torque increases.
Yeah. In this, the load that you connected to the DC machine, it was given that the torque of the fan proportion to the speed square. That's the torque that you attach to the motor. The fan, it needs more torque to get more speed. Yeah, not the machine. Any question on this one? Did you understand the example? Please. Okay. Well, we're done with the DC series motor, and I'm not going to start the DC generator, not to mix everything together. So once we finish the DC generator, make sure that the week after, Friday, not the Friday after finishing, the Friday after, you have time to review, then we'll have exam. All right.
Not Friday, next Friday.
Yes. I can delay it one more week if you like, but I'm worried that you will forget the material. If you wanna delay it one more week, I can do that. Yes.
We have a quiz before, like, next Friday.
Wait.
We have a quiz
Oh, so you like an English language? Okay. Because it'd be a long quiz, because that's like, I mean, we have some DC motor, DC motor generator, yeah. Okay.